to say this meeting is being recorded, but it is. I think I have my computer volume off. All right. Now, one thing I need to discuss is not too much longer before the first test hits. So I want to say a little something about that. Okay. First, so we have 2 tests plus a final. So in a couple of weeks, a little more than 2 weeks, is when the first one will come out. So earlier today, I posted in Canvas on the main home page a practice test and a separate document is the solution. I will have that stuff ready on the my other website that I maintain. I'll post them there after my classes are done today. So as far as the particulars on so this Wednesday, not this Wednesday the 23rd. So two weeks from Wednesday. No later than 5 p.m. is when I will put the test on the home page in Canvas and also on the external site. So you have until this time to submit it in Canvas, and it'll have the same format as what you'll see in the practice test. So I put a total of 7 problems on there, spanning material up to lesson 12, which is what I will cover next Wednesday. So that's the last lesson that's fair game for the test. So those of you enrolled in that 417, you just need to choose 6 out of the 7 problems to work out. Or you can try all 7 and I'll take your best 6. Graduate students, you have to work out all 7 problems. Now, there will be a class period devoted to review, so 2 weeks from today. So what I'll do is discuss the practice test and the solution. So if you have any questions about that, that's a good time to ask them, or any questions about these problems in general. And these are meant to be based on selected problems you see in the homework. So be sure to check this out. Now, some of these problems you'll see will be on things we haven't covered yet, but we'll be covering very soon. Okay. Now, the topic for today is how to solve a PDE that is non-homogeneous. And where this comes about is, suppose you have a PDE that has non-homogeneous boundary conditions. We talked about how you can transform a problem so that the boundary conditions are homogeneous, but that can cause the PDE to become non-homogeneous. And how do you solve that? We haven't seen that yet. So that's one thing. But first, I want to walk through an example of, so this is from a prior lesson on non-homogeneous boundary conditions and how that can go. So here's the problem that we'll deal with. Okay, so heat equation in the simplest form with a coefficient of 1. We're on the interval 0 to 1. And then here are the non-homogeneous boundary conditions. So we have a type 1 boundary condition on the left, where the solution is equal to 1. And then we have a type 3 boundary condition on the right hand. So notice the derivative, du dx, at x equals 1 is equal to 1. And then here we have our initial condition. So what we do is break the solution down into these pieces. So original solution u would be equal to capital U plus some boundary function b of x. So the idea is b of x is the simplest function we can find that satisfies the boundary conditions. Then the original boundary condition, so we can subtract it off, and therefore this solution, capital U, satisfies homogeneous boundary conditions. So B's boundary conditions, B's values is 0. So then we'll solve for this and then add B of x on when we're done. So I set B of x up as a linear function that's equal to some yet to be determined value B1 at x equals 0 and B2 at x equals 1. And that turns out to be this formula here. So here I have this function is equal to 0 at x equals 1 and 1 at x equals 0. And this fraction satisfies the opposite conditions. That's what Lagrange interpolation is. Now, you don't have to do it this way, but there's one fairly systematic way to do it. And then all I'm doing from here to here to here is just simplifying everything. And sure enough, you can see that if I substitute x equals 0 in here, this term is all gone and I get B1. If x is equal to 1, the B1s cancel and I get B2. So now, I'm going to enforce the boundary conditions on this function. So, B of 0, which happens to be B1, must be equal to 1. And then B prime of 1, which happens to be B2 minus B1, must also equal 1. So now I can solve these equations for B1 and B2. And here I have my boundary function. So x plus 1 is a function that satisfies, it's a linear function that satisfies the original boundary conditions. All right, questions?
Because it's B of 0, because that's the first boundary condition, U of 0 and T.
Yes.
That's equal to 1. And then it's B prime of 1 because it's the partial derivative.
With respect to x.
Okay. And there's only x.
Yes. Yeah. So now I need to find the simpler IBDP that capital U satisfies. So it turns out to be the same PDE as the original. Boundary conditions, we have 0 as the boundary values, but otherwise the same form. And then for the initial data, I take the original initial data and subtract B of x off. Now, this happens to cancel out an x plus 1, so we're left with sine pi x over 2. Now, to see why the PDE is the same in this case, it doesn't always happen. Look at capital UT. Well, capital U is little u minus b. I take the derivative of all of that with respect to t. But b is a function of only x. So bt here is 0. So capital UT and little ut are the same. And similar for second derivative with respect to x. So capital uxx is little u minus b, second derivative with respect to x, which distributes to this. But capital B is a linear function of x. So its second derivative with respect to x is 0. So capital uxx equals little uxx. So since little ut equals little uxx, big ut must equal big uxx. So the PDE turns out to be the same. But as we've seen from at least one other example, it can happen like where if a boundary function depends on t, then you have minus the derivative of the boundary function with respect to t as an extra term over here. let's make a note of this here. And assuming the same coefficients. This is this example of both of these things are 0. Okay. Now we have a problem that capital U is supposed to solve. And because it has homogeneous boundary conditions, it's a linear PDE, constant coefficients, we can solve it by separation of variables. So from that, we know that the solution is going to have this form. It's going to be an infinite sum, a linear combination of these functions, capital U sub n, which satisfy the PDE and the homogeneous boundary conditions. These coefficients an are meant to make sure it satisfies the initial condition too. And we assume that capital UN breaks down into a function of x times a function of t. That's the separation of variables idea. As we've seen before, separation of variables, the PDE breaks down into these two ODEs, where k is some constant that's yet unknown. And the ODE for x has the same boundary conditions, but only homogeneous. I won't go over details here, but we've seen there are examples where we have to check. Is this constant k, positive, negative, 0? Cases of it being positive and 0 just aren't going to work out. You can't get a non-trivial solution that satisfies the boundary condition. K turns out that it must be negative. So, going along with that, I write k as minus lambda sub n squared. Because we're going to have a countably infinite set of solutions here, so that's why I have this subscript n. Now, we still don't know what these values are, but we're about to find out. So k equals to minus lambda n squared. I put that up here. So now this is the ODE that my spatial solution has to satisfy. And falling back on what's known about how to solve second order ODEs such as this one, this is the general solution. So anytime you have a solution double prime plus a positive constant times the solution equals 0, then your solution is a combination of sines and cosines. Whatever constant you have here, its square root is multiplying x down here. That's why I made it a square, so I don't have these square roots cluttering things up. So I know I have a combination of sine and cosine, but I've got to find out what kind of combination that will satisfy these boundary conditions. So I enforce the boundary conditions. I plug in x equals 0, make sure I get 0. Take the derivative, plug in x equals 1, also require that I have 0. And what happens is, because of sine 0 being 0 and cosine 0 being 1, I plug in x equals 0, I just get an, so that has to be 0. In other words, there isn't going to be a cosine term. As for a sine term, I take the derivative and set x equals 1, and I get this, that must be 0. Now lambda n is non-zero. Bn must be non-zero, because otherwise I'd have a trivial solution. Therefore, this must be 0. And for that, I have to use the formula for the roots of cosine. Lambda n has to be a root of cosine, therefore lambda n is this. It's an integer plus a half times pi. Those are the roots of cosine. That's just one of those things to keep at the top of your head. n is any non-negative integer, that will cover all the meaningful solutions. Now I can plug this lambda back in here for xn of x, the cosine is gone. So now I have a solution of my spatial ODE that satisfies the boundary conditions. Sine n plus a half pi x. So this function is 0 when x equals 0, and its derivative is 0 at x equals 1. Questions about how this was obtained?
So we have to use the roots of cosine and then take the derivative?
Well, okay. We took the derivative first to apply the boundary condition to this. That gave us this, and that's how we found out that lambda n must be root of cosine. Yeah. So then that gives us this. Then that goes, we go back up to here and put this value of lambda in here, and that's where we get this. Now the ODE for time, that was last mentioned up here. The solution to this, the general solution, is e to the kt. So I have that down here, but k is this, minus lambda n squared, so I fill that in. But I know what lambda n is now from solving this problem, so I fill that in, and here's my time portion. So the thing is, these ODEs, where time and space, if we can solve them independently, it's just that because this one also has boundary conditions, the solution to this one is not completely specified until we have a solution, a full solution to this too. That's what I'm taking into account when I do this. So then I put these two together. Because remember, my solution formula originally is capital U is equal to this kind of sum, where this is a product of function of x times function of t. Now I know what these are, so I can put them in here. And this is what I get. So I have the sum of some constants that are still unknown times my capital T of t, my capital X of x. So this satisfies the PDE, satisfies the homogeneous boundary conditions. We still have to make it satisfy the initial condition. So to enforce the initial condition, we set t equals 0 on both sides. So on the left side, we're going to have whatever the initial data is. So we've got that from earlier. And when we set t equals 0, well, the exponential will just become 1. So all we have is this. So and it turns out in this case, it's easier than in other examples to get the coefficients an, because this is a linear combination of what functions? If I set n equals 0, 1, 2, etc., I'll have sine pi x over 2, sine 3 pi x over 2, sine 5 pi x over 2. So sine of any odd integer over 2 times x. And when your initial data is already a linear combination of those functions, then you can read your coefficients off of this. So, because when I set n equals 0, I have sine pi x over 2. So that tells me that a sub 0 is equal to 1, and that all other a's must be 0. And that will satisfy this equation. So that's something to watch out for. If your initial data is already a linear combination of your spatial solutions, then these coefficients are given away. You just take them from this. Basically, time saver for a test. Now, if it doesn't work out that way, like if I had a very different function, let's say I had x, or polynomial, then there's a then you have to work out an integral to obtain the coefficient an. So that can be a real pain. So then we can wrap up, because now we have, taking this into account, here's my capital U of xt. It's just the first term from this with a0 equal 1. And then I add on my boundary function that was found earlier, x plus 1. So this is a solution of the original problem. And we're done. Any questions about what happened here? Now, in this case, that example, when I made the boundary conditions homogeneous, thankfully the PDE was still homogeneous, so we can just go directly to separation of variables. But that doesn't always happen. So if the PDE turns out to be non-homogeneous, then separation of variables, as we've seen it, cannot be applied directly. But when you do use separation of variables, it can be used. We just have to solve a different ODE in time. So what I'm going to do is, I'm going to explain the process for as general a problem as I can, and I'll be able to provide you with some formulas that help you obtain a solution. And then I'll show you an example. So here we have a more general heat equation that can possibly have variable coefficients. Although pretty much any problem we have, we see will have constant coefficients. And then we have some general boundary conditions. So at x equals 0 and x equals L, we have a boundary condition that is a linear combination of the solution value and its derivative with respect to x. Boundary conditions are homogeneous in this case. And then we have some initial data. Now the PDE is non-homogeneous because of this term. Adding on this given function f of xt that has nothing to do with solution u at all. There's no u in this term. So this is a source term. So it's because of this that if I plug in u equals 0, then this PDE will not be satisfied. So it's non-homogeneous. But knowledge of how to solve the homogeneous version of this PDE, if we drop the f, is helpful to us. So if we are able to solve the corresponding homogeneous PDE by separation of variables, so we have the same old separation of variables happening here. You assume the solution is a function of x times a function of t. Then you end up with same kind of ODEs as before, one for space, one for time. And I've discussed this more general spatial ODE before. It's called a Sturm-Liouville problem. And what's known about this kind of problem is that there are infinitely many values of lambda for which there's a solution that satisfies the boundary condition. And those are called, and these values of lambda are called eigenvalues. Also, what's known about this problem is that the eigenfunctions, which are the solutions, capital X of X, that satisfy this, are orthogonal. So we have this relationship that's satisfied. That you take two different ones, integrate a product from 0 to L, you will get 0. And that's very helpful for enforcing the initial condition. So this is something that's true in general for a problem like this. So, and because of that, we can use an infinite sum involving these functions to describe our solution, knowing that this sum will satisfy the PDE and the boundary conditions. So, if we're able to find these by returning to the homogeneous ODE or PDE, how does it help us solve the original non-homogeneous PDE? So here's what we do. You express your solution as a linear combination of your eigenfunctions that come from your spatial ODE. And the same is true of the source term. These are called Eigenfunction Expansions because capital Xn is an eigenfunction. We're expanding these functions in terms of these eigenfunctions. So we have these coefficients that need to be found. And fortunately, I do have formulas for these coefficients right here. This comes from the fact that these functions, xn of x, are known to be orthogonal. So if I take this equation, for example, and multiply both sides by, say, capital Xm of x, and integrate from 0 to L, because of the orthogonality, I can solve for this unknown coefficient here and here, and that's where this formula comes about. Now, in a general case, these integrals might be a pain. You might have to use integration by parts. But as I've shown you in the previous example, sometimes you can get around having to do this if your uxt or your fxt has a certain nice form. Then you can figure out what these coefficients are without having to actually evaluate integrals. It just depends on the example. All right, so we know how to get these expansions. So then what we can do is, how do we work that into solving the PDE? So here I take the PDE with the source term included, and I do what I described earlier, multiply both sides by a given eigenfunction, xm of x, integrate from 0 to L. Now, my goal here is to, between this equation here and this equation here, I want to get ODEs to solve for these, u n of t. Now, the way I can get that is using integration by parts on this part right here, only this part. And that's what I do down here. I do integration by parts. I actually carry it out twice. Now, I won't go through all the details of this. It's really only its conclusion that you need to apply, but you're welcome to examine the steps later. But to give you some main ideas, think about how integration by parts works. You express the integral of u dv as uv minus the integral of v du. This right here is the dv part, and this is the u part. And because we have boundary terms for evaluating x equals 0, x equals L, when I perform integration by parts twice, I end up with being able to apply the boundary conditions. So I can use the fact that little u satisfies the boundary conditions, and capital Xm also satisfies the boundary conditions, to make a lot of the terms go away. In fact, everything goes away except for this. And notice what happened. Before, I was differentiating little u with respect to x, and this whole thing in parentheses was differentiated with respect to x. Now the shoe's on the other foot. Now it's capital X and it's differentiated with respect to x. And this is differentiated with respect to x. Little u is just sitting here by itself. That's what integration by parts does. It puts the shoe on the other foot. So now, if I put this back in here, then this is what I have. And the reason why this is important is I know what this is and can drastically simplify it. And I'll elaborate on what I mean by that. That this expression right here, go ahead and copy that. That is equal to lambda m mx. Oh, actually, hold on. Check my notation here. Ah, yeah. It's actually equal to minus lambda m. Okay. This is known from the fact that capital X of x is used to solve a homogeneous version of the PDE. So now I can replace all of this by just this. So everything simplifies dramatically, and what happens is, if I replace wherever you see little u and also I see little f, I replace little u and f with these Eigenfunction expansions. And when I do that, I get this. I have a non-homogeneous ODE for use of M of t. Because I know my solution has this form. I just have no idea at the beginning how I'm going to get these. But now I do know. That I just have to solve this ODE. And then the initial conditions for this ODE come from the initial condition of the original PDE, which I want to check. Did I write that down? Oh, dang it! I forgot to write it down. Okay. My initial condition is u of x0 is 5x. So I need to fill that in. Sorry, 1 second. Okay, so now I'm going to have a sum much like this one. Okay, so 5x is a function of only x, so there's no dependence on t here. So these I can figure out at the beginning. Just to get the coefficient an here and the coefficient fn of t here. And an, formula for AN, actually I don't have to give it here because I have given it below. Okay, so here is the initial condition for this ODE. So this has to be worked out one way or another. So now you solve this. So you have a first order initial value problem. This is the sort of thing that you learn how to solve in NAP 285. But you don't even have to remember all that because I've given you a solution formula for it right here. So now we know what this is. In terms of the coefficients of your initial data and your source term in the Eigenfunction expansions. Now, this integral might be a pain to evaluate, but at least you have a solution formula. Okay. Now, here's where, thankfully, I am able to absolve you of any difficulty you might have had following things up to this point. So, I would still encourage, if you haven't trouble diagnosing all this, and yes, it is a lot, I would encourage you to go back and look at these notes later. But everything that you really need to solve, for example, a homework or test problem of this type, is given right here. So what you do is you work these out first. These are the coefficients of the initial data, 5x, in your Eigenfunction expansions. And you do the same for your source term, f of xt. So once you have these coefficients, then you substitute those into this solution formula for coefficients of your solution in the eigenfunction basis. And then you can put these in here, where xn of x comes from solving the spatial part of the homogeneous ODE by separation of variables. So for a general non-homogeneous PDE, associated initial boundary value problem, if you're able to solve a homogeneous version, just as far as, you don't even have to solve this all the way, really you just need the solution to this that satisfies the boundary conditions, but that is a separation of variables exercise. So once you have that, all the solutions of this described, then you can jump directly to here, get your coefficients of your initial data and your source term. From there, get the coefficients of your solution in this Eigenfunction expansion, and you're done. And that's what the whole approach is called. It's the method of Eigenfunction expansions. There are questions about this solution approach? I should mention that if the ODE was homogeneous, that means there would be no little f of xt. So this would be 0. So then that would be 0. You'd only have this term right here. But that's what you get from separation of variables anyway. So you can also think of this as another way of looking at separation of variables. For either kind of PDE, homogeneous or not.
Is that integral gotten by Laplace transform?
Oh, no, it comes from, actually, I don't know if I worked this out, but, okay. Actually, go back to here. Yeah, we're using an integrating factor.
Okay.
Yeah, because what you're doing is, you may remember from your first ODE class, you move this over to the left side, integrate both sides, after multiplying by the integrating factor, and that's where this comes from. I can see why you think Laplace transform because it has a e to the minus st here.
Right.
And then, and s is often used as a Laplace transform variable. Other question? Okay. Here's an example. So here's a problem. Heat equation, general coefficient alpha squared. Here's our source term, a little f of xt, but in this case it just happens to be a function of x. Homogeneous type 1 boundary conditions. And then here's your initial data. Now, we focus on the homogeneous version of the PDE, so we just drop the sign 3 pi x for a moment. And when you carry out separation of variables on this PDE, then this is what you get for your ODEs. And then the boundary conditions from the original problem carry over to these boundary conditions for your spatial problem. Now we've seen this kind of problem before. The interval 0 to 1, these are the solution, general solution of this ODE, sine n pi x. So in other words, lambda is equal to the coefficient of x squared. So those are the eigenvalues. Now, this is kind of a situation where often when you come across this kind of non-homogeneous problem, the corresponding homogeneous PDE you might have solved before with the same boundary conditions, so then you have that solution handy. If not, then you'd have to go through the whole separation of variables process to figure out what this is. But that happens often, like for instance, homework problems that pop up where the homogeneous problem is something you've seen before. So, I need to express the solution, the initial data, and the source term as linear combinations of my eigenfunctions, sine n pi x. Now, in this case, the initial data and source term are of a very nice form, where I can just get the coefficients I need by reading them off of here. So what I get for that is that, well, so from here, I have A1 is equal to 1 for sine pi x. All other a's are 0. Similarly, F3 is equal to 1. All other f's are 0. I have that summarized right here. So there's only 2 non-zero coefficients. So what that means, now the thing is, here's our ODE solution formula with the value of lambda filled in. And also the coefficient alpha squared. Now, okay. If for a given value of n, both an and fn are 0, solution is 0. So nearly all of these will be 0. The only ones that won't are indices where at least one of these is non-zero. So for instance, for n equal 1 and n equal 3, we'll have a non-trivial solution. So for instance, for u1, I have f1 equal to 0, so I won't have an integral. I'll just have this exponential term, but a1 is equal to 1, so I just have this exponential. And then for U3, here's what my solution formula gives me. A3 is 0, but F3, which I've factored out of the integral because it's a constant, that is equal to 1. So now I just have to work out this integral and plug in a limit 0 and t, and this is what I get. All other u's will be 0. So now my solution is actually going to have just two terms. So this term for corresponding to n equal 1. So what I have here is multiplied by sine n pi x for n equal 1. And then for my other term is for n equal 3. So this right here is multiplied by sine n pi x for n equals 3. And that's it. That's the solution. Just a side comment that if I let t go to infinity, this exponential goes to 0. This exponential goes to 0. So all that I have left is this. So this is what the solution converges to over time. Further questions? What it boils down to is being able to solve the spatial part of the homogeneous PDE that you're given. And then how to express the initial data and source term as a combination of those solutions, which are the Eigen functions. Once you have that, you solve your ODE, and then you can put the whole solution together. There'll be a problem of this type on the practice test. You can look at and see how that one's worked out. Any questions? Yeah, stop recording at this point.